All right, this tape is tape 241. It's on radian and degree measure, where you change from radian to degrees, degrees to radians. So let's look at the concept of radian measure. All right, in a circle, you're usually normally ready to deal with 360 degrees. That's where you take a circle and you mark off 360 equal marks around the circle. And if you draw this line back here, that's equal to 1 degree. But now we're going to talk about radian measure. A radian measure is necessary for calculus and other applications in physics, where we have to multiply an angle times a foot or inch or some kind of measurement. And we cannot have a unit as degree there. So what we have to deal with is a radian measure of an angle which has no unit. Now, a radian measure is where if you'll take any circle, small circle, large circle, if you will take the radius of that circle and go mark it off around this side, take this length is the same as this length, and you draw and make an angle here, that's considered to be 1 radian. And it so happens in a circle, any circle, small circle, large circle, if you take that radius and mark it off, it will come out exactly 6.28 times, or what we call 2 pi. If you're familiar with pi, you usually read it as 3.14159. You double that, you get 6.28, so on and so forth. Or other words, if you will take 2 times pi, it will come out to be 360 degrees. If you will take the radius and mark it off on any circle, it will mark off this many times. Well, that means then that 2 pi is equal to the same thing as 360 degrees. That's saying that 2 pi radians is equivalent to 360 degrees. Well, that says then that this number pi, if I divide both sides by 2, okay, is equal to 180 degrees. So pi radians, in other words, if we come back up here in the circle and mark off 3 of these, we'll come out with 3.14 distance around a semicircle. So that tells us then that wherever we see pi in radian measure, it's equivalent to 180 degrees. Well, let's see. If I divide this by 6 and divide this by 6, then that says that pi over 6 is equivalent to 30 degrees. Oh, that's nice. So what we're saying then, and listen closely and then I'll work some examples, is that when we deal with radian measure, which has no units, there's no words, no symbol over here, whereas over here we have 30 degrees and a symbol. When we're dealing with just numbers, we're talking about radian measure. All right, now let's look at the examples and see what the equivalence process is. So we want to change radians to degrees first. Okay, if we want to change radians to degrees, well, to change radians to degrees, we multiply by 180 over pi, because this is 1. This is the same thing as 1. So if we multiply anything by 1, we have not changed its value. Now listen closely to the trick. To change from radians to degrees, we put degrees on top. So we put 180 over pi. If we had wanted to change degrees to radians, we would put the degrees on the bottom and put the pi on the top. That's how simple this chapter is. From changing degrees to radians, or radians to degrees, we simply multiply by 180 over pi, or pi over 180. And that takes care of it. Now I'll talk about some reasoning processes, but still, the mechanical process, if you're just learning, you either multiply by 180 over pi or pi over 180. All right, let's look at example 1. We want to change 7 pi over 6. This is radians. It has no words around it. It has no symbol around it, so that's radian measure. That's important to hear that sentence in a minute, because I'm going to talk about something that doesn't have a pi in it. If you just have a number setting out there. If nothing's around it, then it's radian measure. So if I want to change that to degrees, then I come over and multiply by 180 degrees over pi. Well, those drop out. 6 will go into this 30, and 30 times 7 then is 210. Look at that symbol right there, degrees. All right, so if we want to change from radians to degrees, we multiply by degrees over radians. All right, so our answer is degrees. Now another reasoning process is this right here. What is pi over 6? What is 180 degrees divided by 6? It's 30 degrees times 7 is 210. So if you just reason, anytime you see pi, then that's 180 degrees. And then just go work it out. However, you still need to know this for another example I'll get to in a minute. So don't forget this. Don't think that you can work all the problems by trick method. So know this and then use your smarts and you'll figure these things out. All right, next example. 3 pi over 5. Then we're going to multiply that by 180 degrees over pi radians. So when we get this, we'll get an answer in degrees. Well, let's see. Pi's divide out. 5 will go into this, what? 3, 6. Okay. Then 3 times 36, I believe, is 108 degrees. All right. So that gets the job done. And that's the purpose of this tape, is learning how to get the job done. Not just learning shortcuts. Well, now the shortcut method over here would be this. What is 180 degrees divided by 5? Well, that's 36 times 3 is 108. All right, third example. Minus 10 pi. It has no degree symbol, has no words. There it's radians. Therefore, if I want to change it to degrees, I multiply by 180 degrees over pi. And what happens, this divides out, and we get 1800 degrees negative. Okay. All right, now let's look at example 4 and 5, and these two point out what I was trying to talk about a while ago is, hey, we don't have a pi there, but here's what I want you to hear. Anytime you see a number, and that's considered as an angle. For instance, if you have to find the sine of 3.7, and they don't put that degree mark up there, then that's extremely important for you when you're punching the calculator button. This says that this is radians. This is radian measure. Well, to change radians to degrees, I have to come over here and multiply by 180 over pi. And this time, the pi's don't divide out. Okay, so we just get, well, we multiply the top times the top, and the bottom times the bottom, so this up here will be 666 over pi. And that's an answer, okay? That answer is sufficient. Now, a teacher may want you to divide that out, and so when you go divide this by pi, you will get some kind of a decimal degrees, okay? Comes out about 212 degrees. Okay, just round it off. But this, now watch, this is just an answer. This is not degrees over pi now. This is all of this calculation degrees. All right, next example, number 5, 0.6. Has no degree mark up here, has nothing written around. If this is an angle, then it becomes radians. Therefore, we multiply by 180 degrees over pi. And what do we get when we multiply that by? We get 108 over pi. Now, here's what I want you to see. This times that is 108 over pi degrees. Don't, in the notes, you notice it written like this. Don't read that with that degree mark going just to the 108. All of this divided by that is equal to degrees. Now, I want you to keep looking at that, and I want you to watch the notes. What you get when you divide this is you get a 34.9 3774670. So that's degrees. We want to change this to where we have the answer written as degrees, minutes, and seconds. And again, on all these notes I've been giving on trig, I'm talking about using the TI-85. If you have a different calculator, you can adjust to that. But on TI-85, you need to customize this with the symbol DMS, little triangle out in front of it. And if you will tag that on at the end of the problem, okay, then it will change this calculation over to the degrees, minutes, and seconds for you. Now, while I'm talking about the calculator, there's another customization that you can use, and that is, if, for instance, let's take, we're working this problem right here. If we were finding the sine of 3.7, if you'll customize and put an R in there, then it will automatically calculate it in radians. You don't have to worry about whether your mode on your calculator is degrees or radians. Same thing, if you'll customize your calculator and put a degree mark behind it, then if you're finding the sine of 30 degrees, then if you put the degree mark behind it, then it'll automatically make the mode 30 degrees. That's a precaution, not something you have to do. But a lot of times when you're calculating trig, one from a previous problem you were working in degrees and now you're working in radians, and you punch the button and you get wrong answers. So these are a precautionary concept that you might want to use. So take your calculator and practice some and make sure that you know what you're doing in degrees and radians and that type of thing. All right, now let's look at the next concept. Let's change from degrees to radians. Let's say that we have degrees given and we want to change it over to radians. And this is the purpose of the second part of this tape, is we're going to have to work some stated problems and we have to deal with radian measure, not degrees. So the rule here is then to multiply by radians over degrees. You see, the thing to always remember is what you're trying to get to is got to be the numerator. All right, for instance, if I want to change 2 miles to feet, then what I have to do is say, okay, I want to put feet up here and miles down here. The miles divide out, and what's our answer? Feet. So if I want to change something 2 feet, then they're going to have to be on top. Then I put the equivalents. 1 mile is 5,280 feet. So you go work it out. So what we're saying here is pi radians is equal to 180 degrees. And so if we want radians, we put it on top, multiply, and our answer is in radians. Okay, so let's go look at example 6. We have 45 degrees. So we're going to multiply by pi over 180. And let's see, 45 will go into this 4 times. So our answer is pi over 4. Okay, so that's the mechanical method. Just always works, gets the job done. Here's another way of doing it by thinking process. In a circle, here's pi. Okay, how many 45s are there? Well, there's 1 there and 2 there for 90 and 2 more. So there's 4 of those in 180 degrees. Let's look at 30 degrees. Okay, 30 degrees, there's 1, 2, 3, 4, 5, 6. So 30 degrees would be pi over 6. 60 degrees, well, let's see, 60 degrees, there's 1 there, 2, 3 of them. 60 degrees then would be pi over 3, or 180 divided by 3 is 60. 180 divided by 6 is 30. 180 divided by 4 is 45. So a lot of the special angles that you run across in textbooks, 30, 45, 60 degrees, 210, 150, those type of things, are simply pi over 3s, pi over 6s, pi over 4s. Watch. Pi over 3, 30 degrees. Well, I want 150, then it would be 5 of those. 5 30s is 150. If I want 120, that's 2 60s. So 120 would be 2 pi over 3. I'm sorry, I made a mistake here. I said pi over 3 times 5. I meant pi over 6 times 5 is 150 degrees. All right, catch my mistake here. If I want 150 degrees, that's 30 degree angles times 5. So 150 degrees would be 5 pi over 6. If I want 60 degree, like 120 degrees, then it would be 2 pi over 3. 5 pi over 3 would be 5 times 60, which would have been 300 degrees. Okay. So if I want multiples of 30, like 210, would be 7 pi over 6. You remember that in the notes? We got through working that a while ago. We changed 7 pi over 6, and it worked out to be 210 degrees. If we want multiples of 60, like 240 or 300, that type of thing, then we can use pi over 3. If we want 45 or 135 degrees would be 3 pi over 4. Okay. 5 pi over 4 would be 5 of these, so it'd be 1, 2, 3, 4, 5, so it'd be 225 degrees. So that's concepts you're supposed to pick up on your own. What the notes are trying to say to you is if you want to change from degrees to radians, here's how you do it. Always works on all problems, and that is to multiply by pi over 180. All right? Let's take the next, skip the next example. You can look at it in your notes, 210 degrees. Let's go to number 8 in the notes, 22 degrees and 11 minutes. How do we change this to radian measure? Several ways. Number 1, though, is this is 22 and 11 60ths. Okay, if you want to change from minutes to degrees, you divide by 60. Same concept as a clock. Okay, same thing as if I had seconds over here. If I had 35 seconds, I would divide that by 60. Change it over here to decimal minutes, divide that by 60, change it over to degrees. So therefore, the first thing, from changing degrees, minutes, seconds to radian measure, we have to change it into a decimal, or to what you want to call as a mixed fraction. Then we now multiply that by pi over 180. Okay. So calculator method, a lot of different ways of doing this. A simple calculator method is to do this. Take 11, divide it by 60, add 22, and you now have this answer. And then, of course, if I were you, I would do this, multiply, put it in parentheses, and then you multiply then by pi divided by 180. And it'll give you that calculation. But don't forget, if you have minutes and seconds in here, you must change this into concept into a decimal value. Make this 22 point something, then you multiply it by pi and divide by 180. All right, there's the part of the tape that just explains how to change from degrees to radians. Let's look at some examples of saying why you need to know this. Okay, example 9 says, evaluate these by using a calculator. Well, the mistake that a lot of students make is you don't pay attention to the mode the calculator's in. Okay. Now, the cosine of, there is no symbol right here, so that means this is radians. So therefore, you want the cosine of 0.4276 radians. That happens not to be a very small angle. It so happens that 1 radian measure is 57.346, something like that. Or, I'm sorry, 0.75 something. Degrees, okay? So this is almost half of 57 degrees. So this is somewhere in the 26 degree range, okay? Cosine. Well, here's what I'm saying in the notes. When I put that little R there, I'm saying if you go ahead and put that customized radian measure, you make sure that you're finding the cosine of 0.4276 radians. And that comes out to be an answer of, rounded off, 0.910. It's 0.909994673 actually, but we'll round it off to that. The key that I'm trying to make a point of in this part is sometimes you'll end up seeing in textbooks or homework where you have the cosine of a number over here. It might be 42.76. If there is no degree symbol there, then that means you're dealing with radian measure. And so you better have your calculator in radian mode, or just tag that on the end of it, and it'll make sure it's calculating in radian mode. All right, example 10. Here we have the sine of 3.45. No symbol up here. So that means that's radian. 3.45 radians. You remember? 3 radians. So that's around here. 1, 2, 3, and a little more. Quadrant 3. Sine is negative. You get a negative answer. If you took the sine of 3 degrees, which is right in here, you would have a positive answer. So you must pay attention to this symbol right here. If it's not there, then that's radian measured. So your calculator needs to be in radian mode. So the sine of 3.45 radians, which is 200, almost 200 degrees probably, is a minus 0.304. Okay, now the next 2 or 3 examples are just simply saying that to find secant, cotangent, cosecant, you have to use identities. To find the secant of something, you do not have that button on your calculator, so you must do cosine. So a quick method of doing that then is simply do 1 divided by the cosine of the 0.4276 radian mode, and then hit enter, and you get the answer. All right, so let's look at example 12, 13. Example 12, the cosecant of a minus 3.45. Okay, well now, let's use some thinking here. A minus 3.45 radians is, again, back this way, a little more than 180 degrees, so that's in quadrant 2. So the sine, or the cosecant in quadrant 2, is positive. So here we're finding the cosecant of a negative radian measure and ending up with a positive final answer. And that's 3. That's okay. The cosecant, secant must be greater than 1. So the answer is larger than 1. Sine, cosine must be less than 1. So you should always check your work there also when you're dealing with angles in trig. Well, calculator is simply 1 divided by the sine. Make sure you put the parentheses, and caution, make sure you hit the minus symbol, not the subtraction button. And then simply hit enter, and you have the calculation. All right, looking at example 13, here's where a lot of people foul up when they're not careful of paying attention to the answer. The sine of 30. You should know that the sine of 30 degrees is 1/2. But this is a sine of 30 radians. You know, that's going to keep on going around here about 5, 4.5 sometimes. What we do is we end up around here in quadrant 3 or quadrant 4, and so the answer is a negative. So the sine of 30 radians, so if you get that on your calculator, what happens is you calculate it in radian mode, and you thought it was a degree mode. Okay. Now you can go change the mode, or if you're just working a simple one problem, rather than having to go in and change the mode, then you could customize this and put the degree symbol behind that and get the sine of 30 degrees if you wanted to. Okay. Or you can put the R behind it, and you'll get this answer, which is sine of 30 radians. Okay, now let's look at example 14 and 15, and this is where the application of this chapter is in a lot of other areas that you use trig. We want to find this cosine of 7 pi over 6. So the first step is to change that to degrees. So we're going to go change this to degrees, and that means multiply by what? 180 over pi. Pi is divided out. 6 goes in 80 3 times. 7 times 3 is 210 degrees. Right? That's how it's done. Anytime on your homework problems or whatever that you're given the cosine of these pi's, you know, like pi over 4, then you must change the degrees first. And this is to be done without the calculator, you understand. Calculator, you can just go in here and punch buttons if you want to. But a lot of problems you'll be asked to deal without the calculator. So you change it by multiplying 180 over pi. Then the cosine of 210, okay, is where? 210 is in quadrant 3. How far is it from the x-axis? 30 degrees. So this is the cosine of 30 degrees. In quadrant 3, cosine is x over r. Quadrant 3, x is negative. Therefore, this is a minus 30 degrees. So the answer is minus. Now, the cosine of 30 degrees is where you come and take 1, 2, square root of 3. Cosine is the side adjacent over the hypotenuse, and therefore it becomes minus the square root of 3 over 2. That's how you work the problem without calculators. Now, with a calculator, you're just going to see the answer 0.866. Okay, a negative 0.866. But that's what this happens to be. 1.732 divided by 2 is that 0.866 that you see on your calculator. All right, example 15. The sine of 7 pi over 4. Well, that's the sine of. Now let's do the shortcut method. Pi over 4 is 180 divided by 4. That's 445. I'm sorry, that's 45. 180 divided by 4 is 45. Times 7 is 315. So now we do the sine of 315. Well, the sine of 315 is 45 degrees. So this is the sine of 45 degrees. Quadrant 4, sine is y over r. Quadrant 4, y is negative. Oops. Therefore, this answer is a minus the sine of 45 degrees. Well, now what's the sine of 45 degrees? Well, that's the triangle 1, 1, square root of 2. Sine is the side opposite over the hypotenuse, and therefore the final answer is minus 1 over the square root of 2. And you need to learn to leave it that way. Don't do that square root of 2 over 2 bit. That's only necessary if you have to add it to some other fraction. Square root of 1 over square root of 2. Again, this is 1.414. Divide that in, you get the 0.707, and that's what you would see if you take a calculator and work this out. All right, now let's look at some applications of using this. All right, now let's look at the second page of the notes. It talks about arc length. Arc length. And there's a formula that says the length of an arc, the path this way, on a curved path of something, is equal to the radius of whatever the radius of that circle would be times the angle that is subtended by that arc. Right? So theta is the angle subtended by the arc. S is the length in inches, miles, feet of an arc, and r is the radius. You just memorize this. But listen closely. Here's the reason we have to learn to radian measure. This is going to be inches or feet or miles. And if we multiply that times degrees, then we would say that the arc out here would be degree inches, degree feet, no such animal. Therefore, our theta must be in radian measure. It's a non-unit measure. So then this times inches is inches. This times feet is feet. So that's why in formulas where you deal with angles, and you do not have the sine or the cosine or the tangent, some trig function in front of that angle, it must be in radian measure. All right, so S is the arc length, R is the radius, theta is the angle in radian measure. All right, let's look at example 16 in the notes. 16 says a circle has a radius of 100 inches. A part is how long is the arc subtended by a central angle of 72 degrees. We want to find what this length is in inches, so therefore S is equal to r theta. Well, S, that's what we're looking for, is equal to radius, which is 100 inches, by theta. Oops, you cannot put degrees in there. So in the notes, what I'm saying is what you need to do is to change the 72 degrees to radian measure. If I have degrees there, I need to put degrees on the bottom. And so I end up with the 100 times, what is this? Let's see. 6 will go into that 12. 6 will go into that 30. 2 will go into that 5, so we have 5 pi over 15. And then we multiply all that out. Okay, let's see, that's not right. 6 will go into this, that's 12. 6 will go into that 30. That'll be 6/15, which is reduced to 2/5. Okay. So 5 will go into this 20, and so what we have is 40 pi inches, because this was 100 inches. All right, let's look at the B part. The B part of the problem says, okay, how large is the central angle? So what we're looking for is the angle when it subtends an arc of 3 feet. 3 feet. Now, whoops, we got to watch out. This is inches, this is feet, so we have to have the same units. Well, let's see. S is given as 3 feet, R is 100 inches, and theta, well, we've got to go change this. Either change this to feet or change this to inches. I choose to change this to inches. So that's 3 times 12, so that's 36 inches is equal to 100 inches, theta. So now now watch this. When you divide the 100 inches into 36 inches, the units divide out, and sure enough, you get non-unit measure. No words, no symbols. That's 0.36 radians. That's an angle, though, so that's 0.36 radians. And then if you want to change over degrees, then you can. Okay. All right, let's look now at example 17. Now, you understand these examples are just trying to make up some examples to show you what S, R, and theta. You very seldom will deal with these type of problems in real life, but again, real life problems are a lot more complicated, so we don't want to look at those on these tapes. It says a pendulum of length 60 centimeters swings through an arc of 18 centimeters. All right, so what we have is a pendulum here swinging through an arc of 18 centimeters. Okay, and it says that the length of this pendulum is 60 centimeters. Well, let's see. That's swinging through 18 centimeters here, so that must be S, and that's R. And so now we can come back up here and put 18 is equal to 60 times theta. And so we have the calculation then that theta is equal to 18 divided by 60. Okay, centimeters divided by centimeters, non-unit measure, and so we get that calculation to be 0.3, which is 0.3 radians, which is 17.2 degrees. Okay? All right, number 18. Number 18, I'm using some examples that are similar to the ones you have in the textbooks so that you can use these. So happens some of these examples are in your textbooks, the same homework problems you'll have assigned. All right, number 18 says, how far is it from the equator to level end? What would be the direct mileage if we went from level end straight south to the equator? How many miles would that be? Well, longitudes and latitudes, when we say that level end, and I don't remember the exact value, but the level end is the 33rd parallel. If you're familiar with anything to do with the Korean War, they talked about the 38th parallel. What that is up here from the equator, if you measure off 1 degree, 2 degrees, 3 degrees, and then draw these circles around the Earth, so where level end is, as at the 33rd and a little more, we're at the 33rd parallel. That means the 38th parallel would be somewhere like in the top of Nebraska, or maybe even higher, maybe higher than that. So therefore, that's why it was cold. If you ever watched MASH, because that same area is equivalent to the northern states of the United States. I think Maine, somewhere up there, is like 41 or 42 parallel. All right, so what we're going to do is find this distance from level land down to the equator. So that's the S that we're looking for. We're given that the radius of the Earth, and this is variable. If you look up one book, you may find a different value for this. A lot of textbooks will just round off and say use 4,000. So what's the difference, okay? The point is, whatever the textbook or whatever you want to use for the radius of the Earth, it's not perfect a circle anyway, so we'll use this as the radius of the Earth. And we are given the latitude of level land, but that's in degrees. So what we have to do is multiply by pi over 180 before we use this calculation. Well, again, here you can use your DMS, change all that over to a decimal, okay? Or you can divide this by 60, add it to 22, then divide that by 60, and you'll get 0.3708. Add it to 33, and then you have it. So anyway, point is, this is degrees, so we have to multiply by pi over 180 and get all that calculated, and it comes down to be 0.58243321, whatever, times miles. This is non-unit measure, and then that multiplies out to be 2311 miles. If we wanted to find the distance from level land to, say, somewhere in South America, then what we would do is get its latitude, which would be like, I don't know what they are, like say 20 degrees south. Ours is 33 north, be 20 south, so we would add those two angles, the 20 and the 33, and then we'd use that 53 point something degrees in here. And we could find it. That has to be the distance directly below, not over somewhere. All right, last example on second page of the notes. It says the angle between a chord of a circle and the tangent line passing through one end of the chord. The angle between a chord of a circle and the line that's tangent to the circle at this point is 0.9. The length of the arc subtended by the chord is 18.9 inches. Okay, so the length of this arc subtended by that chord is 18.9 inches. Find the radius of the circle. All right, so what we want to do is to find this right here. Well, let's see. If this is a chord here, if we'll draw from right here to that chord, it happens to be perpendicular, and it bisects it. Okay? So we'll say, okay, well that distance is x there. Now look at this. This angle and this angle add up to 90 degrees. Well, this angle, right over here, this angle 0.9, and this angle add up to 90 degrees because the line tangent to the circle is perpendicular to the radius drawn from the center out to the point of tangency. So, this plus this is equal to 90, and this plus this is equal to 90, so that must mean this angle is the 0.9 also. This angle must be 0.9. So what we have then is this. We have a 0.9 angle here, the radius, and that distance, okay? 18.9. Well, do we? Not quite. You see, the problem is given 18.9 is arc length. The 18.9 is out here. Well, what we'll do is just forget that x right now and extend this out, because if it bisects the chord, it will bisect the angle. Therefore, this s out here will be half of that 18.9. So now let's look at it dealing with r, s, and the angle. So we have this known, we have this known, and we're looking for that. Well, what I have in the notes, I said, hey, let's just forget about doing half of it. Let's just use the whole arc. That's 18.9. So looking at the numbers I have, that's the 18.9. And this angle was 0.9, so the total angle is double it. So I just used 2 times 0.9. Okay, we could have done the other way. We could have used 0.9 and half of this. That's simply just taking this 2 and coming over and dividing it. So it doesn't make any difference. Point is, I've got to use some little geometry concepts to come in here and figure out that this angle is 0.9, therefore the total angle is 2 times 0.9. And so this is, what, 1.8. So to find R, we divide by 1.8 into 18.9, and we get 10.5 inches. Hey, wait a minute. Why is that? Well, this is 18.9 inches, and this is no units. So non-unit measure into 18.9 inches is inches. And so we get that. Okay, now let's look at the third page and do some other applications of radian measure. Okay? All right, let's look now at the third page of the notes. Linear and angular velocity. Okay. Again, this is where we have to deal with radian measure. We cannot use degrees in formulas. Now, what this is linear velocity, which means feet per second, miles per hour, centimeters per second. This is angular velocity. This is the velocity of something rotating. So that's going to be in radians per seconds or per minutes. It's going to be our revolutions per minute, RPMs. Okay? Something that's going around per time. So what we have to do is connect these two up. Well, R is the radius of whatever the object is that's rotating. So V is, in the notes you'll see there, V is linear velocity. That's miles per hour, or mph, feet per second, so on and so forth. And omega, this W, whatever you want to call it, the Greek letter omega, is angular velocity. That's how fast something is rotating in a circular motion. All right, now let's look at the last example of the notes, example 20. Fairly long problem, but it says, the pedals of a bicycle are 7 inches from the shaft. The sprocket is 8 inches in diameter at the pedals. The sprocket at the wheel is 4 inches in diameter, and the wheel is 26 inches in diameter. Okay. I guess what we're saying then is what we have here is the chain up front where our pedals are, and we have the sprocket on the wheel. And what we want to do is to be able to take a linear, say we're going 30 miles per hour, well, how fast is this turning? How fast is this turning? How fast is this turning? How fast are the pedals turning? Okay? Or if we want to do something else, if we had some kind of instrument that, well, if you have a odometer on your bicycle or car also, what it's doing is taking this angular measure, and through gears that have it worked out, it will show you how fast you're traveling linearly. And so this is the formula that works that out, that changes rotational motion to linear motion or vice versa. All right, so this problem says, okay, we want to find how fast our feet are traveling in a rotation motion when we're traveling 30 miles per hour linearly on the road of a bicycle. Okay, so first thing we do, we have to do the wheel to the sprocket at the wheel. So what we got to do is change 30 miles per hour. That's what this wheel is traveling, the bicycle's moving, for this one. All right, so this is a 26-inch bicycle, therefore the radius is 13 inches. So the radius is 13 inches. Okay, we're traveling at a linear speed of 30 miles per hour. Whoa, miles, inches, okay? So what we want to do is change this miles per hour. We want to change it to inches per minute. So here's how we do that. We come over here and we say 30 miles per hour. Now, we want to change miles. We want to get rid of it, so we put miles on bottom, and on the top, I don't know how many inches there are in a mile, but I do know how many feet there are, so I'll take 2 steps. I'll come over here and say, okay, 1 mile is 5,280 feet, and 1 foot is 12 inches. Look what happens. Those divide out. So we now have the problem in terms of inches per hour. Inches per hour. Well, we wanted it per minute, so I'll come over and put, I've got hours on the bottom, so I'll put hours on the top and minutes on the bottom. 1 hour is 60 minutes. So hours divide out, and look what I have. When you multiply the 30 times this, divide by 60, okay, but that's how you change units. If you want to get rid of this one, you put this one on the bottom, and then put its equivalent on top. If you want to get rid of feet now, you put feet on the bottom, put its equivalent on top. 1 foot, 12 inches. Okay, then you divide all that out, and you get all the words left will be inches, and all the words left will be minutes, inches per minute. All right, now let's look back at the problem. And so all that multiplied out was 31,680 inches in a minute. Okay, that's how fast you're traveling linearly. Well, to find omega, I divide 13 inches over here, okay? So I'm going to divide by 13 inches. Look what happens. The units divide out. 13 goes into that. 2, 4, 3, 7 approximately. Nothing. No units. Nothing up here. Okay? So that means that's radians. If you don't have any words left up here, that's radians. So that's 2437 radians per minute. That's 2,437 of these 57 degrees. Okay, that's 1 radian. So it's 2,437 of these, okay, in 1 minute time. All right, so that is how fast, okay, that the wheel is rotating. Well, let's see. Let's do something right now, because some problems in textbooks say, okay, what is the rotational speed of this in RPMs? In RPMs. So to change it to RPMs, then what do? Well, we come over and multiply 1 revolution is equal to what? 1 times around a circle is 2 pi, remember? 1 times around a circle is 2 pi radians. 360 degrees, 2 pi radians. And look what happens. Radians drop out, and so it's 2,437 divided by 6.28 revolutions per minute, RPM. That's why I changed to minutes a while ago. So we end up getting that calculation of 387.5 RPMs. Most of you are familiar with seeing that on dashboards or talking about that. But that's a relationship from changing 30 miles per hour to 387.5 RPMs. All right, now let's look at the next part. That means the chain, if that wheel is turning that way, then that chain is moving at that velocity. Well, the chain is moving linearly. The chain is moving linearly. The wheel is rotating this fast, so that inside sprocket on the wheel is radius of 2 inches. Remember, the inside sprocket on the back wheel was 4-inch diameter, so that means the radius is 2 inches. And the wheel, if the wheel is going around this fast, the sprocket is going around the same speed. Okay, and so therefore we'll use that for the angular velocity of the sprocket, 2-inch radius, and therefore the chain is traveling non-unit here. So this is nothing times inches, so it's inches per minute. So the chain is traveling 4,874 inches per minute. So the chain is moving up to that top into where your pedals are now. So this is traveling at this, okay, linear velocity. So now let's go down and put linear velocity is equal R times omega, okay, of the front sprocket. So the front sprocket is 8 diameter, so it's 4 inches radius. Okay, it's 4 inches, and this is 4,874 inches per minute. So if I divide that into that, okay, I get the 1,218, no units, no words, okay, so that's radians per minute. So the front sprocket is traveling this fast around, okay, so many radians per minute. Then if I multiply that by 1 revolution over 2 pi radians, the radians divide out, and I get RPMs. And so the RPMs are other words, 3.23 revolutions per second. So that sprocket where your foot is going around at 3.23 revolutions for each second. All right, this one example then points out all the things you need to know to be able to work the problems and the exercises and trig books dealing with the formula V is equal to R omega. Just remember this. You can read the problems and know where everything's plugged in because of this. This has to be feet per second, miles per hour. This has to be inches, feet, miles, and this has to be either revolutions per minute. Now, if they give you that to start with, that something is traveling 14 revolutions per minute, RPMs, then what you can do is come down here and put revolution here and come up here and put 2 pi. That will divide out the revolutions and you will get 28 pi nothing per minute. And then you can work with that. And that's what you have to deal with here. Okay, when you plug this in, just like a theta was in that S is equal to R theta part of the tape, this needs to be plugged in as radians per time. Not revolutions per time, but radians per time. Okay? All right, this concludes then the tape on radian, measure, degree, change to radians, radians to degrees.